can we do a surgery in a mechanical way, right? Like that's what surgery is done. And can we develop a non-invasive approach to actually perform a minimally invasive and actually non-invasive way of mechanically destroying the tissue? So that's where the cavitation comes into play. So cavitation is actually basically an activity of bubbles. So we all know bubbles, we see bubbles, air bubbles or vapor bubbles, but it describes the phenomenon of creation and expansion and the collapse of the bubbles. And how histotripsy works is we use focused ultrasound applied from outside the body. So similar to what you use imaging ultrasound imaging machine. So it's the same ultrasound wave. But however, we are focusing that ultrasound wave to a millimeter tiny point inside the body. And we're using ultrasound pressure extremely high, and as high as 300 times of the atmosphere.
Hello, everybody, and welcome back to Chasing Consciousness. So today we have the fascinating invention of histotripsy to look into, which is the non-invasive destruction of cancer cells using ultrasound. That, alongside the other headline news that bioengineers are also using acoustics to pattern replacement heart tissues, makes the field of bioacoustics one of the most exciting for the future of medicine. But it is, of course, the implications of this for the resonant vibrational nature of matter that make this of interest to us here on the show as we attempt to get closer to a true understanding of the nature of reality through our shows on important things like the implications of Einstein's matter is energy equations and the many shows that we have on quantum mechanics. So do go back to those if you're interested. We're lucky enough to be speaking today with one of the inventors of histotripsy, Zhen Xu, Associate Professor and Graduate Chair of the Department of Biomedical Engineering at Michigan University. She's won many awards for this research, including from the American Heart Association and from the National Institute of Health. Now, a quick note to say that all of the books and the scientific papers and the concepts and the points that we're talking about in these episodes are always exhaustively included in the show notes should anyone want to go off and check the research that we're citing here. So please do use them. I'm a real stickler for well-referenced claims. So it'd be great to know that you're taking advantage of all those links. And a quick thank you to you all for your support on the project so far. Do keep spreading the word by sharing the shows with your friends. And if you can give us a 5-star rating on iTunes or subscribe with a bell on YouTube, it really does help me get the show in front of other like-minded thinkers like yourselves. Now, I've been fascinated with bioacoustics and the resonant nature of biological systems ever since I first heard about the importance of resonant frequency in various different types of matter. So I just can't wait to get into this with such a pioneer. So without further ado, let's go. Zhen Xu, thank you so much for coming on Chasing Consciousness. Welcome to the show. How are you today?
I'm great. Thank you for inviting me.
It's a great pleasure to be speaking to such a different type of scientist than the one we normally do. But the implications of this work are so important. I just thought it was really, really good to get you on the show. Now, I love to get started, Zhen, starting by asking my guests about their first deep thoughts about the world, reflections about life, usually when they were quite young, sometime between sort of 8 or 12. What comes to your mind when you start thinking about the first really deep thoughts you had that might be relevant to where your work eventually took you?
Well, my first deepest thought about life actually started when I was 6, so even younger than age. I actually remember clearly because it was the first time I, started reading books and start having question is, why do we exist? Why do we live? Are we even real? How do I know I'm not in the dream or in some program of alien. Well, Matrix came after that. I'm not saying they're copying my idea, but it's just a lot of questions about really the meaning of life. And I remember was struggling with that, and I didn't want to talk to other people because I thought that made me really strange to think about that topic at 6 years old. And after several months, I really couldn't get an answer, about why do we exist, or even is our life real? I started said, why do I approach from the other perspective, which is, what if I die, right? What if I die? What would happen? And it first came to me that I had a really loving family. I'm the only child in the family. And what came to me first is that my parents would be really, really sad. And all the other people who love me, who I care about, would be sad. So it turned out, by the end, a very deep question when I started ended pretty simply because I don't want to make them sad. I live so that, people who I love and who love me would not be sad. And that was a good enough reason for me, at least at 6 years old. And I think that kind of extends to what I do now is for my career, I'm hoping to do something that can help people who I care about to make them live a better life. Even though I still don't know why, I still haven't figured out a large question on the existence of our life and so on. But I do know that I want the people who I love, who I care about, can, live a happy life. And that was the ending of my first deep reflection of life.
Wow, Jen, I mean, that's as deep as it gets, isn't it? And it's interesting how this being part of a network of social connection gives such importance and meaning to people's lives. And I think outside of that, we really would be quite lost, wouldn't we? But interesting, you mentioned helping those people you're interconnected with, because that is exactly what you've done. It's the main topic of today's episode, your invention, Histotripsy, the technique that you've developed that uses focused ultrasound from outside the body to mechanically destroy offending tissue, including cancer cells. And after 3 human clinical trials, you've successfully treated liver cancer. I mean, congratulations on this extraordinary achievement. Perhaps you can start there, Jen, just by explaining what the steps of the process of histotripsy are, and particularly this term cavitation, which seems central.
Yeah, thank you, first of all. I actually want to start with why we even started inventing histotripsy. And it started actually more than 20 years ago, 2001. I still remember the first time Ahi Ludomirsky, who is a pediatric cardiologist. So he came to our research group, and said, we are treating a lot of very sick young patients, and they have heart disease. And we want to be able to perform a surgery. And he, quote unquote, he said, a real surgery where you actually, go in and your scalpel can remove tissue, but in a non-invasive way, because those patients are already sick, and then just going through the very invasive surgery is just really, not helping them as we really want to do. And at the time, and even now, a lot of technology already came out and is still coming out, but they are using different energy to basically heat the tissue. For example, radio frequency, microwave, right? You can use ultrasound to heat the tissue too. And that causes thermal tissue necrosis, basically like you cook the tissue. Then you kill the cells that way by high temperature. But however, the tissue is left there, they're not removed. So that's not a real surgery for some surgery, and that doesn't achieve the purpose. So that started first to make us think, can we do a surgery in a mechanical way, right? Like that's what surgery is done. And can we develop a non-invasive approach to actually perform a minimum invasive and actually non-invasive way of mechanically destroying the tissue? So that's where the cavitation comes into play. So cavitation is actually basically activity of bubbles. So we all know bubbles, we see bubbles, air bubbles or vapor bubbles, but it describes the phenomenon of creation and expansion and the collapse of the bubbles. And how histotripsy works is we use focused ultrasound applied from outside the body. So similar to what you use imaging ultrasound imaging machine. So it's the same ultrasound wave. But however, we are focusing that ultrasound wave to a millimeter tiny point inside the body. And we're using ultrasound pressure extremely high, and as high as 300 times of the atmosphere, all occurring within microseconds. So ultrasound imaging actually uses really short microseconds pulse, so 1/1,000,000th of a second, right? So extremely short. But using that microseconds pulse with extremely high pressure focused to a tiny spot, we can actually create microbubbles out of the nanometer gas pockets that's already in our body. And the reason is we are breathing air. So we actually have air pockets all over our body, but they are typically super stabilized. So you typically don't see anything happening with these gas pockets because their surface tension of those nanometer gas pockets is very high, about 300 times of the atmosphere. So when we actually use ultrasound, and ultrasound is a mechanical wave, it propagates through vibration of the particles. So when you actually vibrate the particles and make them getting closer to each other, that's a compressional pressure and a positive pressure. And when they make them move, vibrate away from each other, that's actually a negative pressure. So imagine that you have a gas pocket, and then you're creating this negative pressure outside that's higher than their surface tension. You can make this gas pocket grow, pop, right? And then when they grow enough, too large, like a balloon, they will pop or they will collapse. And then that growth and the collapse, which occur within hundreds of microseconds, also very fast, it creates this really high strain and strength, mechanical high strength, to actually squeeze a cell next to it when it expands. Then when it collapses, it actually pulls cells apart. So it mechanically pulls cells apart. So basically, those cavitation activated by ultrasound functions as almost a micron bombs in a way, as the size order of a cells. So we are actually dissecting and disrupting cells on cellular level and subcellular level. And that allows us to perform a surgery because we are destroying the cells in the target region with millimeter accuracy. And one great thing about is actually there are multiple great things, but I want to highlight two things. One is the cavitation bubbles are what's called natural contrast agents for ultrasound. So you see them really as really bright spots on ultrasound imaging. So you can see them really nicely on imaging. So this allows the clinician, when they perform this treatment, see where they are treating exactly, because those cavitation bubbles, which is effective acoustic scalpel, they actually appear on ultrasound imaging in contrast to the anatomic structures behind it. So they know what they are treating. And that's very important for a non-invasive surgery where the clinician is not opening the patient. They're not cutting the patient open, but you still have to know where you are treating and still need a very high accuracy treatment. So that real-time imaging guidance and monitoring become a really great feature. And it just comes with the physics here. A second thing is when you think about the conventional interventional approach, which are, including radio frequency ablation, microwave ablation, those are using different energy source, typically putting an electrode inserted into the tissue, and then heat up tissue like I described before. Heating spread, and especially we have blood flow, helps spread the heating further, right? So that's called the heat sink effect. Cavitation, though, is what we call actually a threshold phenomenon, because you have to exceed that threshold, like I mentioned, that surface tension, in order to generate microbubbles. Beyond that threshold, you don't generate bubbles and you don't cause damage. And this allows you to perform a procedure really precisely, because only within the focus and target where your pressure exceeds the threshold, then cavitation microbubbles occur and generated, then you cause damage, and outside you don't. And that's why we said we're performing a non-invasive surgery, because only the treatment region where you intend to treat has cellular damage, and outside the tissues are preserved and intact. And I will stop here for now.
I mean, yeah, you could keep going. It's just such a visionary process. And out of curiosity, just there's always fun stories about this. How did you get the idea? Because there must have been a sort of moment of vision, probably when you weren't in the lab. Do you remember the moment that you got the idea of how this might work?
Okay, so typically scientists like to tell people, we know exactly what happened, right? We understand the scientific process, then we invent this, right? I'm just going to be honest with you that I was a young PhD student, early 20s, and I got into lab, and I had this visionary cardiologist said, hey, can you develop a non-invasive surgery approach? And I thought it was so cool, but I had no clue how this can be done. And then I went through the literature and tried every ultrasound parameters available in the literature, and nothing worked. So I was staring at this, piece of tissue, heart tissue from the pig, right? And one day, and nothing worked. And we had this super powerful amplifier from the lab that's as tall as me. And it runs on 380 volts. It's a monster, and nobody uses it. And I was a first-year PhD student, so I get to use it because no one else wanted it. And I said, I'm just gonna try it. Try something that nobody used before, just for the heck out of it, because nothing worked anyway, right? So I tried really just from nowhere. I came up with these parameters where it required really high pressure, and also I also use really short pulses, because we had some students complaining I was pulsing the ultrasound pulse at a frequency that within the hearing range, and creating this high pitched sound that they were not happy with. So I literally tried to set up parameters to basically amuse myself by using really high power amplifier, and also pulsing it as a rate high enough that it's outside our hearing range, so it would not annoy our lab mates. And that's when the magic happened. I literally was remembering I was doing this experiment in a water tank with a piece of porcine heart tissue, and really just in front of my eyes, I see there is, the tissue debris coming out real time. And within a minute, there's a hole drilled in through that tissue. And I was using ultrasound transducer placed 10 centimeters away. So there was no contact. There's nothing, nothing moved around that. And it's almost like a magic. And then I tried again, and it happened again. And after trying, several times, I started to believe that this is real. This is not just a fluke. And then it took almost 10 years after that to figure out how exactly what happened, what's the mechanism behind that. And another thing is I also quickly broke a transducer, and 20 years ago it was worth thousands of dollars, and I was just in lab. So it also quickly occurred to me that the conventional device at that time, even a state-of-the-art technology for ultrasound transducer would not work for this new phenomenon. We need to really look into improvement of the hardware and software in order to make advancement for this new phenomenon. So histotripsy term was later coined in our lab, and the reason it was coined that way is because all the medical terms are Greek-based. So histotripsy is also Greek-based. It's in parallel with lithotripsy. If anybody knows, lithotripsy is a medical technology using ultrasound to treat kidney stones. And the tripsy meaning mechanical breakdown in Greek. Litho means stone, but histo means soft tissue, right? Histology, if you so basically, we're looking at a mechanical breakdown of the soft tissue, and that's what histotripsy means. It was serendipity, I would say, when the phenomenon was first discovered, but we spent a lot of time afterwards to really investigate and invent and develop specialized hardware, software, as well as really drill down the physical mechanism underlying that phenomenon. And like I said, it took 10 years to do that, another 10 years to then eventually translate to clinical trials.
Oh my goodness. And lovely story of the serendipity there. Is so often the case that these things happen with a combination, an extraordinary synchronicity of different features and things coming together, often mistakes as well coming in there to produce the moment of magic, as you mentioned. Now, crucially, this process leaves no toxic remnants in the body, no heating of surrounding tissues. The debris are just simply absorbed in just a few months. Can you explain how that toxicity is removed by the body? Any complications with relapse, and if there's any sort of collateral damage to healthy cells around it?
Yeah, so first of all, the interventional technology itself, some of them may be toxic, right? So if you look at the current treatment, radiation therapy is one primary treatment, but is ionizing, so it's depositing toxicity into the body. Chemotherapy, even more so, right? So I think the first thing to start with about histotripsy is that we're using ultrasound, we're using sound and the bubbles. You cannot get any more benign than this. This is, this is really just the components we're using here. The sound, the ultrasound has been shown is safe, is not depositing toxicity into your body. And the the cavitation bubbles we generated are utilizing the endogenous gas pockets in our body. So first thing to say is that the technology itself is not depositing any toxicity into the body. And then when we looking at the treatment, right? So let's pick the target treatment for cancer. And the tumor itself, of course, is a disease tissue. And the process of histotripsy is using cavitation to actually mechanically disrupt the tumor cells. So when the tumor cell is still intact, they can grow, they can potentially metastasize. So that's viewed as toxic in a way. But however, when we break up those cells, they are no longer life viable cells. They are acellular debris. So how is actually getting, the body actually removed is that the body view this is actually turned out to be this liquid appearing acellular homogenate, like the soupy homogenate. The body view this acellular debris as basically a waste of the body. So the metabolism process is trying to clean it up. So those debris actually can go through the bloodstream, then go over and reabsorbed by the body. And we have seen in animal experiments as well as a human trial that it takes about 1 to 2 months also for those debris to clean out. And by the end, what you get is something almost really, really close to like a surgical resection where the volume just resected when you go to the targeted volume. In terms of the implication, what we have found out is actually really interesting because we have seen in our experimental study where I'm giving example in this rat liver tumor model with really aggressive metastasis, when we actually treat the animal, we found that if we treat the tumor, it also helps reduce metastasis. We also found in the mouse tumor model, in different models, including melanoma, liver tumor models, and even pancreatic tumor models, where the histotripsy treatment actually help stimulate immune response, both innate and adaptive. And it wonders why. And I think it's related to the debris. And this is my naive take on kind of the cancer immunology, where cancer cells are really good at two things. Again, it's a naive view. So if any immunologists watching this, it's painful for you, please just allow me to express some opinion for just a couple of minutes. So first is the cancer cells have been great at blocking some signal pathway, so our immune system cannot just go in and kill them right away. Because our immune system is supposedly to design to kill any foreign cells or anything that's not good for our body. However, cancer exists there, right? And you have a lot of cancer can progress to really advanced stage. So first of all, it does create a mechanism to block some signal pathway. And that's where the checkpoint inhibitor therapy that's now in widespread clinical use has been successful at to trying to open up the signal pathway to allow the immunotherapy drugs to attack the cancer cells. However, another thing cancers are really good at is they're really good at hiding and escaping from our immune system. So we don't even know they're there, right, to begin with. And I think histotripsy is doing something really, really cool here that I did not envision when we first discovered the phenomenon and invented technology, which is we mechanically disrupt the cancer cells. There's tumor antigen, they are hiding in the cells behind the cell membrane. So now when you disrupt the cell membrane, typically if you use radiation therapy, the ionization can denature the protein. Thermal ablation using heating can also denature the protein, damage the DNA. However, histotripsy is a mechanical process. And we actually intentionally pausing apart give enough time for the temperature to cool down so we can avoid heating. So this mechanical process disrupt the cell membrane, but we think the tumor antigen that behind the cell membrane, they still are preserved and functional. So now you're releasing them, and now they're shouting to the body, "Hey, we're here, we're here." And then even
one question, Jen, excuse me if I interrupt there. One question here: having been destroyed, does it still have the signature that the immune system can identify for further relapses? That's my main question here. Can it notice the actual destroyed cell tissue? Does it still give the signature to the immune system?
Yeah, so we have found that I think it is, there's evidence from the experiment suggests that's a way that even the tumor cells, after they get killed, they are still releasing tumor antigen into the body, that indicating that, telling the body they are there. And even more so, back to the question about how the body clear it, the tumor antigen, the debris actually go into the bloodstream and circulating all over the body. So it indicating to the body, not just at the site of the tumor that there is tumor. The body should search for the entire body, looking for any tumors outside even that treatment region. So that's what we have seen here is that we have seen an immune response where my collaborator, Dr. Cliff Cho's lab, they are measuring the immune response, including a wide range of things from the T cells, then there's natural killer cells, myeloid cells, a lot of different cells that very interesting because he sees that change, really big change of those at the local treatment site. So the experiments was done like the mouse actually had two tumors. He implanted two tumors, treat one. Then he monitored the immune response both at the treatment location and at the other tumor that's not treated. And he observed this immune response at a site that's not treated, very similar to the immune response observed at the treated sites, but delayed. And delayed by almost like 7 days also.
And Jen, what does that mean for long-term relapses? I mean, what's the longest study you've done with these? I don't know if you've done this with the human studies or just with the animal studies. Like, how long have you monitored these subjects after to see if the immune system continued to find any relapsing cancer cells?
That's a great question. I don't have the definitive answer to that question, I have to say. First of all, what we have done were in the rat, we survived the animal up to 3 months, which for the rat lifespan, that's considered to be a pretty long time considering how long they live. But when we treat the rat, and then we actually are looking, and those are the rats with metastasis, where, we treat a primary tumor, then the metastasis goes away, then we continue to survive them for 3 months.
And that is a good sign, isn't it? It's not conclusive, but it's a good sign.
It's not conclusive, but for human patients, I do want to point out that is for the rat study, when we do it, is a very controlled environment, because we inject tumor cells into the rat in order to actually for them to grow tumor, right? However, and they are really young rats, right? They don't have any other health issues. When we talk about human patients, especially there's late stage human patients where their disease can be at very advanced stage. And we're trying to treat as much as we can, but we don't know if the cancer cells can be cleaned up. We don't know. Is this really early stage? And also whether they are in a lot of them in a compromised health condition, and also older patients with more compromised immune system. So it's not clear how laboratory study done in rodents translate to human. Another thing I want to point out is that our current human trials that's ongoing, they are designed to really study the effectiveness of histotripsy as a non-invasive interventional approach, not on the immune study or the immune effects. That's not the focus of the study. And we in the laboratory, what we have found out that the impact of the immune response really is significantly influenced by the dose that delivered. Which is not surprising, right? But we are not adjusting the dose in the current trial to maximize the immune response. And also, I really believe that for human patients who are at a late stage and have compromised immune system, I think to maximize the effect of this immunostimulation that we have seen with histotripsy, we have to combine this with immunotherapy drugs. So I think histotripsy alone is not going to do the magic, especially in those late stage patients we talk about. So that would be something that we are already doing in the laboratory in the animals, but we require additional clinical trials in order to really answer the question you ask definitively.
Well, Jen, do please send me a link to your colleague's study on the immune response paper, because I think it'd be interesting to include that alongside your work. Now, obviously, the headline-grabbing news is the success with cancer cells, but you've also had success with neurological diseases and cardiovascular diseases. Tell us which conditions. I'm particularly interested in the neurological side, because I'm interested to see if there was problems with neurons themselves. Presumably that's a more slippery subject because neurons are so adaptable. How does it work differently?
So we with the brain with a neurological disease, the reason we kind of want to work on this is because that's a holy grail for at least acoustic engineers like me, because there's a skull there to protecting the brain. And so ultrasound actually is known, the bone is a highly reflective and attenuative media for ultrasound propagation. And it's really difficult to do non-invasive ultrasound surgery in the brain. However, it has been done, like there is actually FDA approved MRI-guided focus ultrasound technology using focus ultrasound to heat the target tissue. But that is used to treat essential tremor, where they are treating a very small volume within the central region of the brain that has shown that the ablation of that can treat the essential tremor. However, the challenge for the ultrasound people is that when you're trying to treat outside that little central volume in the brain, then you get closer to the skull, and the skull basically block 80% and more of the ultrasound energy. So if you want to heat the target tissue, you're heating the skull first. And overheating the skull prevents you from treating locations outside the central region or treating large region. And that become a real limitation of using focused ultrasound technology for non-invasive brain surgery. And we really trust when, collaborating and talking to neurosurgeon, that's where we can make an impact, because brain is an organ where it can really benefit from a non-invasive surgery. If you cut into the brain and the neurons are not regenerative, you kill them, they are gone. And the surgery itself can dissect in through the normal tissue to reach a diseased tissue. So the damage to the normal tissue can have really devastating potential impact to the patients. So that's where we started. We are hoping by using cavitation and also minimize the heating, because we're, create long cooling time, we can actually treat different locations within the brain as long as we can create high enough of the pressure to generate that cavitation inside of the brain. And that's the starting point that we started. So really, when you think about it, it doesn't sound great, but it's still the same thing. Basically, when we started, it's similar to when you treat a liver tumor. You just need a really, really powerful device that can treat through the brain. But also other technological challenges is that the skull is not uniform in thickness, so propagating through the skull also defocusing. And the ultrasound, so we also have to creating ultrasound array, really powerful, with hundreds or even thousands of elements to allow us to do sophisticated what's called aberration correction, to allow us to precisely focusing the ultrasound in the brain, still do millimeter accuracy non-invasive intervention through the skull, but knowing that it's a lot more complicated device. So that's what we have created in our lab. We have created this MRI guided. So again, in the brain, ultrasound imaging doesn't really work well. So we need an MRI image to see the brain. So we created this, I think currently the world's most powerful ultrasound transducer, and it's MRI compatible. So we can put in the MRI scanner, and then when we do the treatment, we can see on the MRI image where we are treating, and doing sophisticated things to allow us to targeting precisely in the brain, but generating cavitation and doing the ablation. Initially, we started with brain tumor as a treatment target, and that's natural. And also, we're looking at things like hemorrhagic stroke, so where you have, vessel bursting out and create clotting, bleeding and clotting in the brain, where you push the brain tissue against the skull and causing the patient to have all kinds of issues. So in that situation, we also go in and liquefy the clot to then allow us to put a catheter to drain the liquefied clot out. And that treatment can be done within, minutes to really do a non-invasive treatment and quickly, which is essential for those patients. But those are not reaching but they're still in the preclinical research stage and not in the patients. And the question on the neuron, lately we are starting to look into treatment of epilepsy, so patients with seizures, and starting to have some early evidence that we can impact the functional brain system to potentially treat things like epilepsy and we'll see. We always welcome collaborators and see if we can extend into other applications. But really the main thing here is our goal, at least for our lab, has always been we want to create the best tool we can develop. And then we want to work with clinicians to ask them, how do we use those tools to help the patients?
Well, and it's such a flexible technology. It can be used to change the physical system of so many different situations. It's really extraordinary. So listeners, if you know anybody who could, who may have an application, do please feel free to get in touch with Zhen, because it sounds like they're really, really interested in applying this in the widest possible sense. Now, just as resonant sound can be used to destroy cells, so can resonant sound be used to help pattern the structure of new cells. And this is research that we're seeing in the work of Utkan Demirci and Sean Wu at Stanford Medical School, who've been patterning heart tissue using acoustics. Now, Zhen, I know this isn't your field, but just tell us briefly about their work. I hope that in future, I can get Utkan or Sean onto the show as well to talk about their work. But tell us briefly about their work, Zhen, and how the use of sound to structure contrasts with yours used to destructure, because I think they're related. They're kind of a mirror image of each other, aren't they?
I think their work is really interesting, and it's kind of from the other extreme. We are using sound at really high pressure, and also in a pretty high, in the ultrasound range, which is we're typically using 700 kilohertz or 1 megahertz in the range of 500 kilohertz to so far 2 megahertz range. They are using lower frequency. And the paper shows a 20 to 200 hertz, so much lower, and a much lower pressure. But what they are doing is interesting. That I think this is everybody see the ripples on the water surface, right? So you go in, the vibration of the water can create ripples on the water surface, and what they are doing is that they are using sound to vibrate. The fluid in a plate to vibrate that. And when you vibrate, when you exceed certain frequency, and also exceed certain acceleration, particle acceleration, which is that vibration, then you can create specific patterns on the surface of the fluid. Then this allows you to manipulate the cells in the suspension and make them aggregate in specific patterns. So the stem cells, by doing so, typically in the tissue engineering, people use scaffold to make the cells to grow into a certain pattern, right? But here, the smart thing is that they are utilizing this standing wave, which is called Faraday wave, that formed on the surface, this fluid and the air surface through the vibration that activated by the sound waves, and that using that to create specific patterns that close to heart, allow them to aggregate stem cells in that way to make them form and grow into a heart shape, basically. So in a way, it's kind of, again, a different end, right? We're destroying the cells, but they are making the cell to grow into a specific way that's scaffold free and also biocompatible, because you're not putting in anything, you're just using the cells and the fluid themselves.
The reason, Zhen, I wanted to sort of bring their work into the conversation is because we're very much interested in the nature of reality on the show. And I think it's really important for us to remember resonant phenomena when we're looking for a theory of everything or for any kind of understanding of the nature of matter and gas and empty space, especially when we start getting to the submolecular level. But we'll get there in a minute. Now, all matter has its own resonant frequency, right? Does that mean that different parts of the body have different resonant frequencies? And is health related to how those various resonances harmonize within the body? And if so, could that eventually lead to a sort of new vibrational approach to medicine?
Yeah, so resonant frequency therapy has been interesting idea, and it's does make sense. I think theoretically that supposedly, like you said, different matters, different particles, different even different cells could have its own resonant frequency. So there has always been theory that the cancer cells can have very different can have their unique resonant frequency that could be different from normal cells. And if that's a case, then you could potentially use that resonant frequencies to destroy the cancer cells while not hurting the normal cells. So it certainly has been a theory around, and people look into this. And however, is this myth because it has not been supported by any scientific data or clinical trial. So even though there is this theory that seems to make sense, and there's people who have been talking about it, so far, at least at this time point, we haven't seen scientific research or clinical data to support how that can be done effectively, at least that time point.
So the ultrasound community haven't been discussing this as an actual option. You haven't seen anybody trying to measure and to model the resonant frequencies of these various different types of tissue in the ultrasound community.
I don't think it's a lack. I think there are people trying. I'm saying that we haven't seen successful data yet. Yeah. So I think they have been trying, and I actually have in the past thought that there was some promise of generating data to support that. So I'm certainly not ruling it out. I'm just saying that at this time point, we just haven't seen successful data. But I don't think this idea has been given up in any.
I guess I have this sort of this image, which I'm trying to work out has any basis in fact, which is this idea that if different organs or different areas of the body have their own resonant frequency, and for whatever reason, whether it be biochemical or even related to the state of mind or the fight or flight response, for example, certain areas of the body might over time become less resonant, that might have negative health outcomes. I mean, is there anything to that kind of logic, or is this again something that's been theorized but we don't have any data for?
Yeah, we don't really have any data, but I also have heard stories and which I don't know is true. There were some investigation at some time point, and again, it's a myth that I haven't really seen any really scientific data publication. But people were talking about using sound vibration of the body or organ, and potentially can be weapons. That you could have the sound at certain resonant frequency that can go through walls or anything, then use it to really damage internal organs and. Well,
I think Havana syndrome. Something there was this odd story. We'll link it in the show notes. I don't know the details, but there was an attack on an embassy in Cuba, and they had these extraordinary things of these embassy staff getting these really weird symptoms, feeling sick, feeling dizzy, falling over, and this kind of thing. And that it was theorized that there'd been a microwave weapon had been used. So it's a whole other area, isn't it? Now, I want to get your opinion, Jen, on a really famous quote that I'm sure many, many listeners will have heard as a means of sort of asking you, what are the sort of wider implications of your work of the use of ultrasound as a non-invasive technique in general. It's from favorite physicist Nikola Tesla. If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. Do you think he was right?
I love the quote. At least he definitely is right when it comes to my work. That's what I work on. Really when you think about what we're looking at here, the vibration, right? So that's how actually sound propagate. Large part of my work is to really solving the work where how can we propagate sound and in a more controlled and precise way so that we can reach the target we want to reach, right? So certainly the vibration is a big thing. The energy, right? There's propagation. We're propagating the energy. We're propagating sound energy in the case of histotripsy, and how much energy can we propagate where we have to overcome the energy loss due to the vibration through those particles in our body or in acoustic coupling media and all that. Energy is a key. Like I said, in the brain, right, we really always strive to do is to trying to get enough of energy in. The one goal of the work is always like how can we deliver the most energy to the target region, and the frequency is certainly key. That if you talk to any acoustic physicist or engineer, where the frequency is a key in many ways. So give you an example, ultrasound, the higher the frequency, the smaller the wavelength. And the wavelength determines how accurate you can perform a treatment. For example, we can use really high frequency, like 10 megahertz, and we can perform surgery in with micron accuracy. But however, higher frequency also results in faster attenuation because you vibrate so much faster, so that friction, right, of the part between the particles, you can quickly absorb that energy away. Therefore, if you want to reach a deeper tissue, we actually would prefer to use a lower frequency because then you have less of an energy loss. So it's always a struggling between the, how can we get enough of energy in, but with good enough accuracy. So that's the tweaking of the frequency that we do in order to get this to work. So the components you're talking about, energy, the quote, energy, frequency, and vibration, those are key components of my work that I encounter every day. I love it. That summarizes it.
But obviously, Tesla was, I think, using it in a much, much wider sense. Now, obviously, you've mentioned a few things out of your field that you've read about, that you've known about in your long years studying science in a more general sense. What are the wider implications for the nature of biological tissue and perhaps even matter in general from your work?
Yeah, so I would say that, there's deeper thoughts about acoustic as a field, right? And the energy field, vibration field, and how that could impact the nature of the matter, right? Whether it's about creation of nature of the matter and or maintaining potentially the structure of matter and so on. Certainly it's not my daily work, but that's one of the things I really like when you mentioned Stanford's work, where they are using acoustic field to doing patterning of the hard tissue. In a sense, they are using this to maneuver the formation of tissue structures and envisioning that which, I always wonder that if you think about how the life begins when we all start early on from singular cells, then eventually grow from many, many cells to human being, right? Or animal and come through, really that's life, where life begins. So at the early stage of that, I always, wonder that, is that how the energy or the field, or, through different ways, sound or electricity or magnetic field and all that, is that how the surrounding kind of this world impacts the formation uh, of life, or of formation of new matter that way? Because that's a way that can be manipulated, right?
Well, that's sort of, it really reminds me of strong, powerful stories from Hindu mythology, that the order of the universe is held together using fields of sound and vibration. Even in Christianity, in the beginning was the Word. There is this ancient reference that seems to be quite cross-culture. Is it so incorrect to say that resonant fields are responsible for maintaining the structure between molecules? That we, just through our perception, listeners, we've got 2 great shows on this. Anil Seth, the controlled hallucination, and Don Hoffman on user interface theory, both of which are arguing that the world is not as we see it. This perception of matter, liquids, and gases, could it not be that we're perceiving a deeper sort of resonant field reality that is maintaining what we see as structure between molecules?
Well, I think it's like I said, I think it's very possible. Again, I don't have scientific data, so as a scientist and an engineer, that I always hesitant to say this is a case when I don't have scientific data. However, I do again, wonder that I do think there's some energy field at the beginning that does. Just think about human being, right? Like we start with 2 cells, right? A sperm and egg. But how do we all grow to have 2 eyes, 1 nose, 1 mouth? And why do the life that consistently form the life they are? Why do dogs look like dogs and why do cats look like cats? And there must be something, I think more than DNA. I think the DNA certainly, the genetics certainly play a role, but I do think there is something else that's going on there that impact the life, impact matter. And I actually, this is not sound, but recently I came across this very interesting study by Tufts researchers from Tufts University, where they are looking at bioelectricity. Right, they found out that when the tadpole, at the beginning, when they form, before they even have eyes and nose, there is some transient electricity change. And they found that transient electricity change occur at the location where they later form eyes and nose. And it seems like those are not necessarily, like later, needed to maintain their structure, but at the beginning they seem to be there to help signal where the eyes should be and where nose should be. And they did this even a provocative experiment where they then thought, what if we manipulate the electricity signal? So they actually manipulated the electric signal at the back of a tadpole, and they actually end up growing an eye-like thing at the back of the tadpole, right? So this is not necessarily sound, but this make me think about the energy, right, in the field that you manipulate at the beginning when the life forms, that may have implication beyond just the DNA to really are important and guide, and we just haven't really been able to catch that, just because it can help maybe really just at the right specific timing and very transient, and they all need to come together in a way, just like you talk about resonant frequency, so to speak, in a way that can potentially impact how the life and the matter forms. But it's a topic that I think we are growing in this age. What's really great for scientists like me is that we are having more and more tools we have at our disposal to observe phenomenon, things that would not be possible 100 years ago or even 10 years ago. And so we're lucky in this way. You know, we have ways where we can do imaging, we can do testing that does not necessarily require even incision, right? Just like what we're doing with histotripsy, that we also are building ultrasound transducer, you know, because you can imaging too, right? So we have more tools like, you know, my work on ultrasound, like sound you can apply and manipulate in a super precise way, as well as you can detect it. So I think now we are getting the tools to start allowing us to decipher some of the really the mystery in the universe, in the life that we always wonder about. But I do think this is going to be the golden age that going forward, just because now we have the tools.
And Jan, this is so wonderful that you've mentioned this, because I've been hunting. There was an important book in the late 80s and early 90s of a scientist who sadly is now dead. And he wrote an important book called The Bioelectric. And it was very controversial at the time. He was looking at reptiles, and he was finding exactly what you've just mentioned from this TUFTS study. So Jen, please send me the link to this work, because I haven't been able to find anybody doing work on this. So I really need to speak to these guys. And I think he was a biologist, and he was theorizing that these fields were fundamental to the way that, in this case, reptiles were regenerating limbs after they'd been lost. And he was studying the electromagnetic fields around those creatures as they were regenerating. And he was finding exactly the kind of data that you're talking about. So please send that to me. I'm so happy that you mentioned that. But the reason I ask this in more general is it seems to me that both from Einstein's famous relativity equations, E equals mc squared, that confirm that matter really is equal to energy in some sense, and obviously the important work in quantum mechanics that confirms that all particles organize themselves into quantum fields with their energy and information and even location uniformly distributed, in the field, that information is uniformly distributed. It all points towards a field-based understanding of matter. And as such, that field might be in some way fundamental to matter, rather than the matter generating the field in the first place. Now, perhaps the question here isn't which is primary to which, and they co-arise, but it seems to me important. Now, I know we're pressing you to speak about something that's outside of your field again, but what are your speculations, just to close, Jen?
Yeah. So again, I just want to say this, just my thoughts, and not supporting.
No, you're a professional.
but does make me wonder. When when the Earth was first formed, right? You go through that process of big explosion and form, this the Earth planet and everything on it. And I have to believe that at the beginning, before many matters were actually formed, there was some sort of a field and some sort of energy that within could be really short time period, under very, very specific circumstances, that formed the Earth that we're living on and making this a unique planet that's from at least the other planets we have been able to explore. There's a lot of many planets we haven't been explored, but this is a planet that livable for human, right? But it has to be at the genesis of this, place that at the beginning, there's something very special, unique, that allow it to form the way it is formed, that has a certain oxygen level, right? Have certain, we have 70% of the water, right? So why do we have all this? And there's certainly chemistry, physics, and a lot of things going on. But how and what kind of field and the energy that was at the beginning, and so that he actually creates the solid and the liquid and the gas in the way they are. I do feel that there is this certainly unknown out there that we don't know yet. But
your idea reminds me of
yeah.
stem cell biologist Bob Lancer's biocentrism theory. I'm not sure if you know about that, Jen, but he's theorizing that actually space-time is generated by life rather than life evolving in space-time. And I think it's a very, very interesting idea. And listeners, I have heard your many requests for me to get him on the show. I'm still trying, and it won't be long before we get to speak to him. In the meantime, there is a physics show with one of his collaborators about that, the physics implications of the biocentrism theory. So, Jen, thank you so much for waxing lyrical there. I know it's slightly difficult for professional scientists to talk about scientific affairs outside of their field. So I really, really appreciate you speaking about that publicly. And I really appreciate you following me down this road of sort of intuitive logic that I'm trying to follow here on the show. And you just must send me that Tufts University study, because I am desperate to talk about this with some people who can, really, really tell me about the data rather than getting carried away by the wonderful possibilities. So just to close, Jen, what's next? You spoke about many things you're working on in the lab. What's the most exciting thing and the thing you're making funding applications for at the moment? What's the next step?
Well, so we are fortunate that conducting a human trial, but we're still far away from getting this to widespread use for the patients, and that's really my goal. And I think this will be my life quest for the next probably 20 years in order to fulfill the full potential of histotripsy. Just like we talk about, there's this immune stimulation that we have seen in the lab. How can we trying to maximize that and then apply that to the clinical use that can benefit patients?
What's the real block here for something like that being used instead of such invasive and dangerous therapies? I mean, obviously, absolutely, we know how good the cancer treatments are doing against such a difficult enemy, but they really are leaving people with very, very serious collateral damage, a lot of toxicity. Why would it take such a long time as 20 years to get this into the hospitals as a treatment?
Well, it's actually pretty common for disruptive new technology.
Disruptive?
Yeah, well, disruptive in a way in terms of technology, right? It's very different from what people are used to use. So when you're trying to ask clinicians to use this technology, they are really doing something very different from their current practice, that they are used to. They receive many years of education from medical school and residency. Now you're handing them a tool, say, hey, use this, which is something that they never used before, right? But
does that apply to the healthcare providers as well? Does that apply to the market?
Well, there's certainly we have to have Food and Drug Administration approval clearance to actually sell this machine. And Histotripsy, the company that building it, the machine and the sponsored clinical trial, is in the process of waiting for the FDA to review this and to get approval. And after that, there's also other issues that reimbursement that you need to get approval from the government so that the patients and the clinician can actually getting paid for, well, the patient can have something that help them cover the cost, but clinician get paid to perform the procedure. But on top of that, FDA, the reason they have this existence is what they want to make sure is safe, effective, rather than just saying, hey, use it on the patients, right? So even though we have been having some success in treating the liver, we want to expand it to other organs. We're starting trial in the kidney, in the pancreas soon, but there are many organs we can treat that require additional clinical trials, as well as some of the organs may require a specialized histotripsy device designed for those. And the immunotherapy combination trial is a separate thing that, again, has to go through the process of getting really the preclinical data to apply the right dose, for example. Then we have to go to the FDA to do another trial, right, specifically on immunotherapy. Again, as a scientist, that we have to have real scientific and clinical data before we can make this as a widespread use and tool for the patients and the clinicians. And then we're working hard on this, and I know that there's still going to be a lot of work that we need to do. And I will be very happy one day when I retire, I look back that see that we are saving patients with a technology that I invented with a team together at early 20s. If I can do that when I retire, I will be really happy. And I do want to, by the end, acknowledge the team at the University of Michigan that really we work together on this technology, including a lot of people from Charles Kane, Tim Hall, Johnson Sukovich, Cliff Chu, Michelle Lala. I'm missing a lot of people, but again, it's a team effort. So, yeah.
Well, I cannot think of a much more noble quest for a career, Jen. So you must be so proud of your work. Keep it up. And let's hope that by the time you retire, this has been rolled out to the wider public. Zhen Xu, thank you so much for your time. Speak soon.
Thank you, Freddie.